Hello, this is Rick Powers coming to you from my home office for Western Technical College. Introductory Statistics, Introduction to week number 12. What I'm going to do is share my screen with you so you can see some notes that I made regarding this topic. So, if we ask the question, what is the purpose of statistics? The purpose of statistics is to know what to expect. And when we want to know what to expect about something, there are two main ways in which we do this. The first way that we talked about earlier was that of using the confidence interval. If we use the confidence interval, then what we're doing is we're actually finding out a measure of a population based on a sample, which is great. We ask the question something like, what do we expect in terms of how many people are going to have side effects for a particular medicine? We don't have everybody, but we have a group of people that we say are a sample. And then we say, okay, a certain percent of this sample have headaches when taking this particular medicine. So then we would say that's from the sample, but what would it be for a population? Well, a confidence interval will tell us that. Hypothesis testing, however, is where we try to prove a difference. And that's what we're involved in right now. We have different hypothesis testings that we've been doing. And so I want to speak specifically about what that means. And what we're doing when we use hypothesis testing is that we have one particular group that we're interested in, and we take a sample of that group. And then we have another number that we're comparing, which is given to us from a previous situation. So we're talking about comparing two populations. One of them has a given number. And what does that specifically look like then? When we say, how does this work? We're talking about a null hypothesis, which might be that a proportion is equal to 30% or 0.30. And then we would have an alternative hypothesis that a proportion is greater than 30%. So this number, this 30%, that has to be given to us. And so like it was a national survey of how many people owned cats, then that would be the 30%. But then what we care about is some other group like Western students. And so this here, this P that we're talking about, this is talking about Western students compared to the given number, the 30%, which we got from some other measurement, whether it's a national survey or something. And so what we're interested in then is if our group, the Western students, actually have a proportion greater than 30%. But we can't know that because we can't measure all Western students. So then we have to use a p hat. The p hat, which comes from that same group that we're interested in, but it's only a sample number. It's p hat. And then by using p hat and the p, the sample measurement compared to this other population measurement, then we say, is it unusual for us to get such a sample? And then that's going to give us, through some kind of a formula, by using this information, we get a test value. And then once we have a test value, then that is, in this situation, we're using Z. We get a test value of Z, which is telling us, is it unusual to get such a thing, such a sample. And then when we say, well, what's the probability of such an unusual sample? That is our p-value. And the p-value is going to be the area. In this case, because it's greater than, it would be a right-tailed area. That's going to be this area out here, based on the formula for the test value and then the p-value. Now, when we use something like SALT or software, we can just put in the information for the sample. We can put in the information up from the hypotheses, and then it will tell us what's the test value and the p-value. And then we say, if this p-value is very small, then we can make a decision either to reject the null hypothesis and prove the alternative. That's what we want, if the p-value is very small. If the p-value is not small, then we do not have enough evidence to prove anything. So then we cannot make a decision. Now, we've gone through all that, hopefully, in terms of how to do that with proportions. And we are only using one sample. We're using a sample from a particular group, and that sample is a p-hat, a measurement of a proportion, and we're comparing it to some given number that came from somewhere else about proportions. Okay, so that is what we've done so far. We've done the proportion, but now we're going to do the same kind of a thing with the mean. So this was all with proportions. And then when we say, how would this work with the mean? Now we're going to have a population mean equal to something like 35. Let's say it's the age of people in a particular online forum. And we say, well, I think the average of people in a forum like this should be 35. But then we take a sample to try to prove something, like maybe, hey, it looks like this is a younger group, so that would be the mean less than 35. And so we could try to prove it, and certainly it could be less than, it could be greater than, we don't know. But then what are we going to use? We're going to use a sample mean, x bar, to do that. So the sample mean, x bar, is going to come from a population, and we're going to ask the question, is this population different from what I said it would be? Is it less than 35? Are these people on average younger than I expect them to be? Okay. So then we're going to get another test value again by using a formula, or by just putting it into SALT. We get a test value, but the test value is a t number. It's not a z number, because when we're talking about the mean, there's a certain level of uncertainty, as you may recall back when we talked about this, with regards to the confidence interval, and that is because we're using S, the sample standard deviation. So the sample standard deviation with this sample mean, and using those in relation to this hypothesized mean, that's going to give us our t-value, which once again is going to go on our graph of t. If we had a graph of t, it would look like this. And in this case, it's a left-tailed test. And then that would also give us another p-value, which we can then use to make our decision. If the p-value is low, then we know it was unusual to get a sample that was this different. And so we can say, well, if it's unusual to get such a sample, then our population is actually different from 35. So we prove the alternative if the p-value is low enough. So far, so good, I hope. But then we have another situation. And this last situation that we have is now where we're going to be not using just one sample, but we're actually going to be using two samples. So we're using two proportions. We have two different proportions that we want to use for this. So now it's not that we have just a number up here, we're going to have two different proportions. Now, I'm going to show you how this works. If I have a P1 and a P2, then normally we would consider them to be equal to each other. And then we would say, are these two groups the same? Like if I'm measuring how many people got headaches in Wisconsin versus Minnesota. Well, I mean, you can argue the fact of Wisconsin being more headache producing than Minnesota. But if you're going to try to prove that, okay, then you would say, all right, I'm going to assume that they are the same. And then I'm going to take samples in order to try to show that for however this works, that this P1 is going to be greater than P2. So then this is what I'm trying to prove. I'm trying to prove the population numbers to be different from each other. But I don't have the actual population numbers. I have P hat 1 and P hat 2. And so those are taking the number observed out of the total observations for both Minnesota or Wisconsin, whichever. And it doesn't matter what order they're in, as long as you're consistent, okay? If you say Wisconsin is P1 and Minnesota is P2, then Wisconsin would be greater than Minnesota, okay? However, what often happens here is that we don't use the actual P1 and P2 being equal to each other. What we're going to have is P1 minus P2 to be equal to 0. And then P1 minus P2 to be greater than 0. So if we ask the question, is P1 equal to P2? Well, it could be. If that were the case, then what's the difference between them? 0. And then here, if P1 is greater than P2, what's the difference between them? Greater than 0. So then this is how something like SALT is going to be set up. They say, what's the difference? What is the hypothetical difference? In this case, it would be 0. And then what are we trying to prove? We're trying to prove that the difference is greater than 0. Now, when you put this into SALT or some other software, what you'll see is that it's still talking about z-scores. We're still using the z-score as the test value, and then that will generate the p-value, and then we can make our decision. All right, so backing up here, what's happening this week is that instead of just going with two different proportions, or I'm sorry, instead of using one proportion in relation to a given number, we could also have the mean in relation to a given number like this. And then we can also do hypothesis testing with two samples that represent two populations. And then if they're equal, the difference is 0. If one is greater than the other one, then that's greater than 0. And certainly we could flip it if, say, we just say Minnesota is P1 and Wisconsin is P2, well, then it'd be less than, if we have evidence that Minnesota has a lower proportion than Wisconsin. So there we are. There you have it, hopefully. Certainly, it's relatively complicated, and I doubt that you've seen this stuff before, but the idea is that if you have any questions, you let me know, and you can contact Julia in the Online Math Center. And hopefully, as you've become more comfortable using SALT, you'll be able to put the numbers in the correct places. And if you have any question at all, please let me know. All right, best wishes for this week.